Alright, last piece with the exponentials, and then I need to stop making videos today because I'm tired and grumpy. But we need to tackle and talk about these last couple of exponentials, which are going to be weirder because they're not base e. So if you look at this first one, we have a 2 to the 3x power. And we got to learn how to take the derivative of stuff like that, or how to integrate stuff like that, right? Sometimes we see stuff that's not base e. I would guess that like 98% of the time it is base e, which means we have e to the stuff, or we have a log base e, aka we have a natural log. But we could have a log base 5 also, and we got to learn how to deal with those other bases as well. And it's pretty easy. There's just like one extra little piece in the formula that you're going to need, and then otherwise it's the same. Okay, so let's do a little bit of pre-cal review, and then we'll get into the calculus, and then we'll be done. Good riddance with the exponentials and the logs. Now, here's your change of base formula. You can change the base from any log, from whatever that base it gives you, into whatever new base you desire. Typically, the bases we like are base e, so we like natural logs, and then also we like base 10, so we like common logs. So base e and base 10, those are the two that we like because the calculator has pre-programmed buttons on it for the common log, the log, and for the natural log, ln. So if you're going to change it, right, you would typically change it into either a base e or a base 10, but you don't have to. You could change it to whatever you want. And then here's that change of base formula that you would use. Okay, so here we go. Let's do this first example. It says use your calculator if needed, and then give your answer correct 3 decimals. We're going to do the exact solution, and then I'll show you the calculator. Okay, so if we have an exponential, what we'd want to do is rewrite it as a log. So you could think about it as taking a log base 2 on both sides, or just rewrite it as a log. You do a log base 2. A log base 2 of 45 is going to be equal to 3x. You're just rewriting it from the exponential to the log, and then you would just have to divide by 3. So I know that x is going to be 1/3 log base 2 of 45. Now that's your exact solution, but if it wanted you to get the decimal, you'd be like, okay, how? How do I do that? How do I do a log base 2? I know I could divide by 3, but how do I do a log base 2? If you look on your calculator, we have the log button, and right below it we have the natural log button. There is a way in your calculator to change the base. You just have to know how to hunt throughout your little programs and through your kind of just different menu options in your calculator. But there's not a really nice specific button, right? There's a log button and there's a ln button, and we like those because the calculator can do them really quickly and really easily. There is a way your calculator can do the log base 2. It's just a little bit harder. So we're just going to use the change of base formula instead. Okay, so I've got this 1/3. I guess it's going to go out in front. And now what I could do, this is the log base 2. I'm going to just change it, right? I'm going to change it to natural log. I like natural log the most. So I'm going to change it. And what this formula says is whatever base you have, and whatever's inside of that log, it doesn't matter. You can take a log of the inside over log of that original base, right? So I kind of always envision the little like fraction bar here. You do log of this over log of this, and you can pick whatever new log base you desire. Now I'm going to choose base e, so I'm going to have an ln, and 45 goes on top, over ln of 2. So I'm using my change of base formula. Log base 2 of 45, this is the same thing as log ln 45 over ln of 2. Right, now I can do the ln of 45. Ln of 45. I could also do the ln of 2. And so there we have it, right? We could take this answer. Don't forget, we would still need to divide it by 3. And we could get that this final solution is 1.831. Okay, so we could do that. The calculator doesn't easily do the log base 2 of 45, but we could switch it into our natural base. So we could use natural logs, and then we could get it. Or if you don't want to, you could also have switched it into your common logs. So I could have done log base 10 of 45 over log base 10 of 2. You could have switched it and done the common logs instead of the natural logs. Let's look at what would have happened there. Log base 45 divided by log base 2. And then let's see, divide it by 3. It's the same thing, okay? Whether you switch it to the ln or whether you switch it to the common log, the log base 10, it doesn't matter. Okay, you can switch it to whatever base you wanted to. I could have changed this base 2. I could have changed it to log base 8 of 45 over log base 8 of 2. Why you would do that, I don't know, that's weird. You wouldn't really want to, but you could. You could change this original log, and you could pick, right? That n is your choice. You can pick it and change it to whatever new base you want, but typically you would desire the n to either be 10, your common log, or you'd like it to be e for your natural log. But you could pick, and you could change your original log, and you could rewrite it as this quotient, and you could pick whatever new base you desire. But typically we would do either the natural log base e, or we would do the common log base 10. Now let's quickly look at this, right? These two things are equal to each other, right? Obviously the final answers end up giving you the same thing, so those two things are equal to each other. But is log 45 the same thing as ln 45? Let's think about it. Log 45 versus ln of 45. Oh no, those aren't the same. Okay, they're different numbers. So the fractions give you the same ratio, but the tops aren't the same, and neither will the bottoms be the same. But think about it like this. Is 20 over 2 the same thing as 10 over 1? Yes, those ratios are definitely the same. Is 20 the same as 10? Surely not. Is 2 the same as 1? No. But is the ratio 20 over 2 the same as the ratio of 10 over 1? Yes, right? The ratio is the same. So even though these individual components are not equal, the ratios of them will be. And that would be true even if you switched to like a log base 17 of 45 over a log base 17 of 2, the ratio would still work. Okay, so the change of base formula is nice. You could pick whatever new base you want, but typically you would choose either a base e or base 10. All right, last one, we have a log. We're going to rewrite it. You could either think about taking a 5 to the power of both sides, or just rewrite it as an exponential. So I'm going to have 5 to the third power equals the stuff on the inside. 5 to the third power equals the stuff on the inside. That's 125 equals x minus 2. Add the 2 over. We get 127. That one's pretty easy. So there's your Precal review. Now let's look at how to take the derivatives of this stuff. Now let's kind of recap what our original rules were. Okay, so if I have ln of x, the derivative is just 1 over x. Right? Easy. If I have ln of something, the derivative, whatever's inside the log goes to the bottom. Chain rule goes to the top. Okay, not too bad. A little bit harder, but not too bad. Now let's look at this rule. If I have a log base a of something, let's just do a log base a of x. Whatever that x is would still go to the bottom. And then since that's just an x, you don't need to do chain rule. Now the only extra thing, since that's a log base a instead of a log base e, right? Whatever this number is, you would just need to do an ln of that base, and then it would go in the bottom. Okay, so it's the same formula, right? ln of x still puts the x on the bottom. Log base a of x still puts x on the bottom, but then to account for that base being something else, you just need an ln of that number, and logs put that term in the denominator. Here, if I had a log base a of anything, whatever that inside stuff is would still go to the bottom. Chain rule would still go to the top. That's what your du dx is, chain rule. But then to account for this being a weird number, you would just have an ln of that base on the bottom. That's all it says, right? You just have this one new extra piece. If it's a base other than e, you just need a ln of that base on the bottom. Okay, let's look at the exponentials. Let me flip it over. For our exponentials, we know the basic parent function. Let me try to keep this on the screen. The derivative of e to the x is e to the x. So if I had e to the u, the derivative would be e to the u, and you would just multiply by the chain rule derivative, right? Whatever hits down because of the chain rule, or whatever, right? You know the derivative of e to the u is e to the u, and then you just watch out for chain rule. Now, if I have a to the x, so if I have some other base, the derivative is still going to be that exact same thing, right? The derivative of an exponential is that exact same thing, but since that was a base other than e, you would just have that one extra piece that you would need in your formula. You'd have to multiply by the ln of that number. Remember, the logs put it in the bottom, the exponentials are going to multiply by it. Logs divide, exponentials multiply. Or if I had an a to the u, right, where that u is just some other weirder function, you would still just say the derivative of that exponential is itself. You would still do chain rule, and then since that's just a weirder base, you would just do it times ln of that number. It's not a hard formula. Okay, it's a very easy formula, in fact. Let's go practice, then we'll look at the third formula. If I have 2 to the x cubed, let's do a basic example first. Like, what if I had y equals, how about we had just something like, how about we had just 3 to the x power, right? What if we did one without any chain rule? The derivative of 3 to the x power would be 3 to the x power. Then I would just need times the ln of 3, right? That's it, right? If it was a e to the x, it would just be e to the x. Since it's a 3 to the x, right? Since it's that other number besides e, you would just need to account for that other base by putting an ln of that base, and the exponentials would multiply by it. Okay, so here if I had 2 to the x cubed, the first thing you would copy is, what was that exponential? And then you would do chain rule times 3x squared. That's literally nothing different as if it would have been an e. Now the only thing that's off, because it's a 2 instead of an e, is you should put times ln of 2. Right? And then this right here is the derivative of that weirder other base. You just have the one new part in the formula. Right? You just have to multiply by an ln of that number. Or for a log, you would divide by it. So here, if I had something like log base 5 of x, right? If that was my original, I could take the derivative. Whatever's inside would go to the bottom. If it was just an x, you wouldn't need chain rule. And if it was a log base 5, you would just need an ln of 5 on the bottom. Right? That's not super bad. Now, if it's a log base 3 of stuff, my formula tells me whatever that inside stuff is, right? Logs put that stuff in the bottom. Chain rule would still go to the top, right? So if that was an ln of this stuff, we would be done. But since it's a log base 3, all I need is an ln of 3, and the logs will put it on the bottom. So there's just the one extra piece in the formula, right? That ln of the base, exponentials multiply by it, the logs divide by it. So for the logs, that ln of the chunk goes to the bottom. Okay, now let's think about this integration. So let's think about 2 to the x, and let's think about integrating it. And let's kind of revisit these formulas. I know if I had something like, obviously we know the derivative of e to the u is e to the u, therefore the integration of e to the u is e to the u plus e, right? That's really easy. We've done the exponentials already. So if I have a to the u, we just did this. It's a to the u times ln of a, right? That's what the derivative is supposed to be. So if I was integrating, and if I had a to the u times ln of a du, like if you had this number like you're supposed to, then it would integrate a to the u plus c, right? Because you're just working backwards. You would just be undoing the derivative. Now, let's think about something. If I was integrating, and if that ln of a, now ln of a is just some number. It's usually some weird ugly decimal, or it's usually just written like ln of 5. They don't usually write the ugly decimal. But if this number is supposed to be there, but is not, just think about it, just like use substitution. To account for the number that's supposed to be there, but is not, right here if it's missing, you would account for that number being missing by having a 1 over that number on my original function. And the 1 over on my original explains why the ln of a isn't there on my derivative. Because if this was my original, and then if I took the derivative, look, you have the coefficient, then a to the u is a to the u times ln of a. That 1 over explains why I just had the a to the u by itself. The 1 over cancels with the part that was supposed to be there but was missing. That's all it says, right? If the ln of a was here like it was supposed to be, right? So this could either be on the left side, in which case it's just fitting the formula, you're working your way backwards. But if you're integrating some other exponential with the weirder base, then you just think, hey, you're supposed to have an ln of something here. To account for it not being there, you just need a 1 over that number on your original, right? So this next example, it's 2 to the x. I know 2 to the x, if I were to take the derivative, I would have 2 to the x ln of 2. So if I was integrating, I would really want that ln of 2 to be there. And if it was there, then it would spit me back. I'd have 2 to the x plus c, and then I would be done. But since this number is supposed to be there, but it's not, you could just have a 1 over ln 2, and then that 1 over ln 2 on the original explains why the ln 2 was missing from the derivative. That's literally all this one says, right? It's a little bit tricky. Most of the time, whenever these other bases come up, it's usually derivative questions. But if you have to do an integral, you should be okay. 1 over ln 2, and then you have your 2 to the x plus c. I usually will write it 1 over instead of having it all combined. But if you wanted to put 2 to the x over ln of 2, like if you wanted to actually have it fit that formula, that's okay. I usually write the 1 over because that kind of reinforces more closely with what we saw when we were doing u substitution. All right, last one. Here we would need to do the u sub first. So there's my u. U would be x cubed. The derivative would be 3x squared dx. There is no 3, so the u sub is going to kick out a 1/3. So got 1/3, 3 to the u du. So this is a weirder base. I know the integration. I have the 1/3, so that's nice. I know it's a exponential, so I know it's going to also have that same thing plus c. But then since this was a 3 to the u, I know if this was my original function, I would have had an ln of 3 here. Since the derivative is missing the ln of 3, I know that original has to have a 1 over ln of 3. Okay, and then we could reverse substitute. This is going to be crazy, right? You could leave it as 1/3 and then 1 over ln of 3 times your 3, what was the u? X cubed plus c. Or if you wanted to, you could combine it. You'd have 3x cubed over 3 ln 3 plus c. Look at all those 3's, and then none of them cancel. You could put this 3, and you could have ln of 27 on the bottom if you wanted to. You could have ln of 3 cubed, but you have all these 3's, and none of them should cancel. Okay, it's kind of a weirder, uglier one, but that's okay. All right, and speaking of weirder and uglier, we're going to do just one more example, and then we'll be done. Now, this stuff right here, you don't really need to worry about it for a while. Right, so this process called logarithmic differentiation, you really don't have to stress a whole lot about it when you're working in like calculus 1. Okay, but let's think about stuff. If I have something like x squared versus 2 to the x, right here when I have the variable in the base and then the constant is the exponent, that's called a power term, right? And for the power term, I just use the power rule. Let me kind of don't look at that anymore. We're looking here. Okay, so something like x squared is a power term. We use the power rule. We know that. Something like this, where the base is constant, and then the exponent is what's variable, that's an exponential term. Now, we could live with either exponentials or logs. We know how to take the derivatives of both of them. But what happens when I have variables in both the base and the exponent? Right? Because that's not a power term, and that's not an exponential. So I can't use the power rule, nor can I use the exponential rule, because that's not a power term, and that's not an exponential term. And you can only use those two respective rules when they apply. So how do I somehow take the derivative when there's variables in both the base and in the exponent? You don't really need this process now, but it's a neat little skill. So I always like to show it just so you can keep it in your back pocket and you can pull it out later in the future and you can impress either your classmates or impress some pretty girl or something, or your professor, and you can show them how it's done whenever there's variables in both the base and in the exponent. And it's a weird little process involving taking a natural log. Taking a natural log first is a useful, nifty little skill that sometimes will solve quite a lot of problems for us. So let's look at it. Taking a natural log on both sides. Take a natural log. So I have ln of y on the left, and then we'll have an ln of whatever that stuff on the right was. Okay, so I took a natural log on both sides. Now, here I'm going to have an implicit differentiation. Remember, the goal is still to find y prime, so I'm still going to have to take the derivative and then get it in terms of x. So I'm going to have an implicit differentiation. But at least now, this is something that I can do, because when I've taken the natural log, what can I do with this exponent? right? Since I have the property of natural logs, now that exponent can be brought down to the same level, and then I can have something like this. ln of y equals, you had x minus 3 times ln of x plus 1. And now you no longer have any bases and exponents out. Everything's kind of on the same playing field. You're going to have a product, which means you're going to have to do product rule. And you're going to have an implicit differentiation also. So it definitely makes the calculus a little bit harder. But at least it's calculus we can do. Right, so now we'll go through and we will take the derivative. The derivative of ln of y is 1 over y prime. That's your dy dx. Over here, you're going to have to do product rule, but that's okay. The derivative of the first is 1 times the second. You just copy it. Plus, the derivative of the second would be 1 over x plus 1 times the first. Okay, I'm going to rewrite this just quickly. I'm going to, instead of writing 1, I'm just going to drop the 1, and I'm going to combine all that stuff. So I have 1. Actually, no, we're not. I'll combine it in the next step. Okay, so we have the 1 over y prime, right? And it's equal to all of this stuff. And then what I would need to do is I would need to get the y prime by itself. So I'm going to multiply this y over. So now that's gone. I shouldn't put an x probably. I should just cross it off. So I took a natural log. That brought it down to the same level. Then I took the derivative. It was implicit. And then I had to do product rule. That's okay. Kick the y over. Now I've got an equation for y prime. But it says find y prime in terms of x. So it doesn't want this thing. Right? It wants it to only be defined by the variable x. So here we go. Right, here's how we could write it. I'm now going to just copy this stuff, ln of x plus 1. I'm going to combine all this, so plus x minus 3 over x plus 1. And then instead of the y, what was the y equal to? Remember the question told us? The y was, I keep making it more diagonal, and I'm trying to make it less diagonal. Okay, Mr. Belt. The y was x plus 1 to the x minus 3 power. And so that is what your derivative would look like. It's kind of ugly. You don't usually have to do stuff like that very often. But if you do have variables in the base and in the exponent, you would actually need to go through this process called logarithmic differentiation. Right? You have to take the log first because that enables you to get everything on the same level playing field. It kind of makes it a little bit harder because it's implicit and it's a product rule, but both of those things are skills you should have. And so taking a log first kind of enables us to then do the rest of the calculus. It's a neat little skill. Taking a log first brings everything to the same playing field. You don't really need that a whole lot this year. Just kind of keep it in your back pocket, keep it in your little toolbox of little skills and techniques, because it is something that comes up periodically in your upper level maths.